All right, this is part 3 of section 5.3. We're trying to determine the graph of this equation. F of x is equal to x minus 1 raised to 3 times x plus 2 raised to 2. Okay, now to find the roots or the x-intercepts, what I'm going to do is I'm going to set each one of these equal to 0, and I can do that because finding the x-intercept is setting this equal to 0, and then notice I've got two things multiply together and they equal to 0. So I'm just going to break them apart, set them equal to 0. Okay, so cube root both sides. So x minus 1 equals 0, so x equals 1. Square root both sides. So x plus 2 equals 0, so x equals negative 2. Or a very easy way of doing this when you have it's factored like this, you just take what's inside, change this negative 1 to a 1. Take what's inside, take this positive 2 to a negative 2. So I have x-intercepts at negative 2 and at 1. Okay, so at negative 2, let's look at the multiplicity for negative 2. Let's get rid of this. Okay, so for negative 1, it's raised to an odd power. So we know that it's going to cross the x-axis at that point. So here's our x-axis. And since it's raised to 3, it should look like a cubed function, so something like that. And then at 2, it's raised to an even function, so it should touch the graph and then bounce off of it. So it can either go, say, this direction or the opposite direction. Okay, and we would need more information for that. But on the homework, you'll have graphs that you can pick from and choose which one is the correct one. This is the graph of that function. Notice how at 1 it looks like this, looks like a x cubed function. And we also have at 2, look, it's going down right here. We could also find the y-intercept of this as well if we want to graph this from scratch. Okay, let's look at in behavior. So if the degree is an even number and you have a positive leading coefficient, then your function will be going upwards for negative and positive for x. If x goes to negative infinity and x goes to positive infinity, the function will be going up to positive infinity. You have an odd degree and a positive leading coefficient. Then as x goes to positive infinity this direction, your function will be going up. If it's going to negative infinity for x, then your function is going down towards negative infinity. If you have an even degree and a negative leading coefficient, then as x goes to negative infinity, your function will go to negative infinity. As x goes to positive infinity, your function will go to negative infinity. If you have an odd degree and a negative leading coefficient, as x goes to negative infinity, your function will go to positive infinity. As x goes to positive infinity, your function will go to negative infinity. So let's look at this right here. So consider this polynomial, and we need to find out the degree of this polynomial and the leading coefficient of it. So the degree of the polynomial is 5. This is the highest one. And the leading coefficient is negative 4. So I have a combination of a negative leading coefficient and an odd degree. So I'm looking at this right here. So as x goes to negative infinity, the function will go to positive infinity. Okay, so positive infinity. As x goes to positive infinity, our function will go to negative infinity. Okay, so this will be negative infinity. And that's the answer for that right there. Same thing here, we need to find the leading coefficient, and we also need to find the degree. All right, so to get the degree of this, I'm going to look at this x right here is being squared, so x times x. And then I've got a negative right in front of it, so this would be a negative x squared. We would eventually multiply this times this term and this term. Okay, so I'm just going to look at when it's multiplied by the 2x squared, because I'm looking for the x raised to the highest number. Okay, so this would be negative 2x raised to 4. So that's my leading term. Okay, so I have an even number here and a negative number here. So that would be this case right here. So both of them would be going down to negative infinity. So this would be negative infinity, and that's it. Okay, so we could write here 4 and negative 2 just to fill those in. Now let's talk about the intermediate value theorem. Let f be a polynomial function. The intermediate value theorem states that if f of a and f of b have opposite signs, then there exists at least one value c between a and b for which f of c is equal to 0. Okay, so this is just saying a y function at a y function at b. Okay, so if we call this right here f of b right here, so that means at we have a y value that's close to 1. We'll say it's close to 1. Okay, our x value is 3. Okay, and here at a, that we'll say it's about 2, and our y value is negative 3. Okay, so we have a y value of 1 here, a y value of negative 3 here. Notice that they are opposite signs for your y values when you plug in those x values. Okay, so that means that we're going to have an x value that when you plug it in, y is going to be 0. So right here, and let me move this. So right here, y is 0 when you cross the x-axis. It's like when you're finding intercepts. Okay, so if they have opposite signs, so they're saying if you have a y value up here and you have a y value down here for your function, and that function is a polynomial, which we know it is smooth and continuous, then that means that somewhere in here it has crossed the x-axis to get back from that negative up to that positive or vice versa. So we can be guaranteed that at least one value, some x value, that when you plug it into your function, it's going to give you 0, which means you have a root or you have a x-intercept. So determine if the function of f of x is equal to x cubed minus 5x squared plus 3x plus 6 has at least one 0 between x equals 1 and x equals 4. So all I'm going to do is I'm going to take f of 1 and plug that in. So that'll be 1 minus 5 plus 3 plus 6. So that will give me, that'll give me 5. I'm going to go back and I'm going to plug in 4. So 4 cubed minus 5 times 4 squared plus 3 times 4 plus 6. Okay, 4 times 4 times 4 is 64 minus 5 times 4 times 4 is 16 plus 12 plus 6. So 64 minus 5 times 16 minus 80 plus 12 plus 6. Okay, so that will give me 2. Now notice both of these are positive, or they're the same sign. So because they didn't change from a negative to a positive, one's not negative, one's not positive, we can't determine if there is at least one 0 because we need opposite signs for the intermediate value theorem to work. Now let's look at this one. So I'm going to do the same thing. I'm going to plug in 1 for my function. So that'll give me 7 minus 19 minus 1. So that will give me negative 13. And we'll plug in 2. So that'll be 7 times 2 raised to 5, which will be 32, minus 19, 2 raised to 4, which will be 16, minus 2 times 2, which is 4. Okay, 7 times 32, 224 minus 19 times 16, which is 304 minus 4. So it looks like that's going to be negative 84. So notice they're the exact same sign. They didn't change, so we cannot determine if it has at least 1, 0 because they are the same signs here. Now say I tried x equals 3 instead. So I'm going to keep this answer here, and now I'm going to try 3. Okay, so that's going to give me 7 times 3, or 3 raised to 5. It's 243 minus 19, 3 raised to 4. 81 minus 9. Okay, 7 times 243, 1701 minus 19 times 81, 1539 minus 9. Okay, this will come out to be 144. Okay, so now I've got a negative and a positive value. So I can say that at least 1, 0, or x-intercept is between 1 and 3 because I got a negative and I got a positive, or I got opposite signs.